Okay, welcome back in. We are going to do electromagnetic induction, and that's a mouthful. And so let's give you what the keys are. Any changing electric field produces a magnetic field. Any changing magnetic field, and I shouldn't say induces. Oh, and I left the word field out. Field induces a magnetic field. Any changing magnetic field induces an electric field. So, how can I make that happen? Well, this change in fields is called flux. Flux. So we have formulas. Electric flux is electric field strength times area of the region that's being affected times the cosine of the angle between field and area. We'll get to that. We don't use the cosine very often. Likewise, if we're doing magnetic flux is magnetic field strength times area times the cosine between the two. Okay? So in your class, you do not have to worry about this piece very often at all. Okay? That's typically a value of 1, so you don't have to worry about it. Now, so what that gives us is EA and BA. So let's look at how this is going to work, and let's talk through some examples. And so I'm going to look at number 30 to start with. So let's get over here. Let's zoom that up for just a minute. Let me move my toolbar out of the way. Okay, so let's stop the share for just a second. Okay, put that down. All right, so in this case, you have a magnetic spring. And I want to talk about the ideas of induction. Then we're going to write them down. But here's what we get. We have a metal spring, a slinky, if you will, that's been wrapped around. So, slinky wrapped around like this. That's what we got. Which of the following will not cause a current to be induced? Okay, so we're working with, we want to see if current miraculously appears. That's our mental phrase for induced. Surprise, it's magic. There's now an electric field there. It only occurs if you change the magnetic field strength, you change the amount of area, or you change the orientation. So that cosine angle is actually an orientation piece. So, what would cause me to have a current? Well, one of the things I could do, particularly if this is a spring or a slinky, is instead of making this loop, I could make let me hold this with 2 fingers. I could make a bigger loop, a bigger circle. If I make a bigger circle, my enclosed area is larger. If my enclosed area is larger, then I have more flux. I have created a flux where I had none before. Okay, so I got somebody come in the room, so just hang on for a second. Sorry, we got some interruptions, so I didn't videotape the interruptions, but I'll get back to where we're going. So when we're looking at the slinky, the ways that you can make a current flow where there is no current, you may notice there is no battery on this spring. There's also no plug-in on the spring. So how in the world can we make electricity flow when we don't even have a source to push or pump the charges or whatever? Well, the source becomes the magnetic field, and if I start moving the spring in and out, What I'm doing is I'm exposing the charges to that. The charges inside the wire perceive that as their magnetic field is moving. Okay, the magnetic field perceives that charges are moving around in my field. And so because of that, I see you moving, I get an induced field. So if I was to take the slinky and spread it out like this, I would increase the area. Increasing the area causes an induced current to occur. So there will now be an induced current that wasn't there before. And that induced current will also make a new magnetic field that was not there before. So the wire with the charges go, ooh, we're moving, make a magnetic field. The magnetic field goes, ooh, charges are moving, stuff is moving, make an electric field. So it really will feel like magic, and it's okay to think of it as magic because magic is really just something you don't understand very well. But that's one way we can induce a new magnetic field and induce a new electric field. The second thing you can do to have that happen is you can actually turn the knob on the magnetic field up. So if you make the magnetic field, if you've got it where you can turn it up or turn it down, like a knob on a dimmer switch for electricity, you can turn the magnetic field up. If you make the magnetic field get stronger, then all the charges go, ooh, the magnetic field is changing, I should run around. Now I get a current. So the magnetic field induces electric field and the charges start to run. If I turn it down, the charges still start to run because it says, ooh, changes in the magnetic field. Magnetic field induces electric field. But to the magnetic field, what it sees, the reason it believes the current is there is because there was a new induced, the charges go, I'm moving, I'm running, I'm doing my thing, and now I'm going to produce a magnetic field that's out there. So because I'm electricity and I'm changing electricity, I'm going to make a magnetic field. And so every time you change anything about a circuit, or you change an orientation, or you change an amount, you have created what we call flux. You've changed the field somehow. And as soon as you change the field, you get an electric current. It acts like there's a battery in the circuit now. It acts like a circuit. Well, it's just really a coil of wire. By the way, the fancy word for this is a torus. T-O-R-U-S. And the last one, of course, is we can spin the magnet. So we can have our circle like this, but we can turn it. So no field lines pass through, all the field lines pass through. No field lines pass through, all the field lines pass through. That's changing the orientation. That's what the sine bit does on this. So the sine bit does the orientation. So on number 30, what will not cause a current to be induced? Well, changing the magnetic field causes one. Rotating the spring about a diameter, turning the spring, does. Moving the spring parallel to the magnetic field. If I just take it and I leave it in the magnetic field and I move it this way, as long as it doesn't leave the magnetic field, no induction. We haven't changed strength size, we haven't changed area, and we haven't changed orientation. So C is the correct answer for number 30. Okay, now I'm going to minimize this. We're going to go back to our whiteboard so that we can then work some more problems. And let's shrink this down a little bit so you can see the whole questions. Okay, so let's come over here, and I'm going to give you the two laws that go with the flux. So when you have flux, you will get an induced voltage that is change in flux over change in time. So you get an induced voltage, and the induced voltage is going to be BA cosine theta divided by time. You get a negative sign. We'll talk about what the negative sign does in a minute. You get an induced, sometimes the AP test will sometimes use this as well. Electromagnetic force. It's not a force, it's a voltage. You will get a new magnetic field or a new electric field that appears because of this. So there'll be an induced magnetic field and there'll be an induced electric field. We'll talk about how to get those. There will also be an induced current. So all of those things will happen. So what does the minus sign tell me? The minus sign, this is called Faraday's law. And Faraday's law says anytime you have a flux, you get voltage and you get current and you get new fields. You get new fields, always, both kinds. You get new current that wasn't there before, and you get new voltage because there's current. The current is coming from that fake voltage, this induced, this magical voltage we just did. Okay, then there was a guy named Lenz, and to keep this short, Lenz's law says the new stuff opposes the changes. The new stuff opposes the changes. So, let's do this. If my magnetic field strength went up, my new fields will be magnetic field that goes down, opposes the change, electric field that goes in the opposite direction, and current that goes in the opposite direction, and voltage that goes in the opposite direction of whatever you were doing to start with. So what we're going to do with all these problems is we're going to figure out how it starts, and then we flip it all because everything does the opposite. Now, you have to be careful. This opposite sometimes means you reinforce, you replace the missing part, and sometimes it means you literally oppose it, you try to force it back down. So Lenz's law says the new stuff opposes the changes, and that's what the negative sign says. So this is just, I'm throwing this at the wall, we're going to see what sticks. It's not terribly difficult. What's difficult is keeping track of all the pieces. That's really what's difficult. So let's look at one over here. And I'm going to show you this one. So on that one, I'm not going to worry about that one. I'm going to do this one. Let's do number, what is that? Number 44. Let's look at number 44. The plane of the loop is positive, and we're going to have a square loop. So we've got a square loop inside a magnetic field. So the magnetic field goes to the right, and they tell me there's a current going clockwise. So I've got magnetic field is to the right, and I have a current carrying wire. I have a wire in there that's got a current of 2 amps. So I'm just using this information, and we're going to talk about what happens. I'm not going to do any of the math because you can look up the formulas. I'm not going to do any of the math right now. I just want you to get the big ideas. The big ideas because you're writing about this. So what happens if we decrease B? What happens if I make my magnetic field strength get smaller to all those parts? Well, there's a new magnetic field, so we got induced magnetic field, induced electric field, induced current, and induced voltage. If you can get all the words right, if you can talk about the words and stuff, you'll be far better than me spending a lot of time working math problems that you can look up the formulas to. I will show you the math formulas, and I will do examples, but I'm not going to do a ton of them. Spend a lot of time here. So what happens if we decrease B? B is getting smaller. So what is my induced going to do? I don't want you to get smaller. I want you to stay what you're doing, status quo. So the B induced will help the original field. So in this case, the magnetic field was going to the right, so the induced field will point to the right. You're weakening it, and it induces a magnetic, that change says, ooh, make all these new things, and the new one will try to hold the magnetic field up. But remember, these are all responses. Things don't happen instantaneously. So by the time the magnetic field, the induced field comes about, the real field's gone down, and now you're just responding to it, but you're always a step late. You're always a step late, so the induced always lose. These always lose at the end. They try to keep everybody status quo. They try to keep us where we were, but they're always going to lose because they're a reaction to a change, not a source of a change. Okay, so that's what our induced electric field is. So now we have to ask ourselves, in this wire, which way would the electric field go? Well, in the picture they showed the wire going, the current's going like this. So I need an induced electric field that will make the current go in the, this is clockwise, so the induced current is going to also, what's going to happen here? What's happening? Our field is getting weaker. So what's our induced current going to do? It's going to help the original current. So it's going to be clockwise. The induced electric field is going to have to help the original field. And for any part of the wire, it would be like left to right, top to bottom, right to left. So you have to kind of, so your field lines in here would sort of point, on this part the field goes this way, on this part the field goes that way. Here the field goes this way, here the field goes this way. So it's going to reinforce that because it's going to help the original field. So it will continue the field. It will try to continue making that field, producing that same field to keep us there. And then the voltage is actually just literally, in this case, we would have a bigger B in our original area, and our orientation is the wires are perpendicular to the field. This is a right angle. So the cosine, so this is cosine 0. I know that's weird. It's a right angle, but it's a right angle. The current, let me see if I can say it like this. The current is this way. So the area vectors are, the current vector goes this way. Current vector goes to the right. Magnetic field goes to the right. So those two options are to the right. So this is cosine 0. They're parallel, if you like. And so the current there will just be whatever you change B to times whatever A and how much time you did that. So that would be the math piece. And we'll talk more about how you get those organizations. Really what you need to keep in mind is that with electricity, everything in electricity works parallel to the field. With magnetism, you need everything to work perpendicular to the field. And so that's kind of how the two differ. They do all the same kinds of things, but magnetic fields work on your perpendicular side, and electric fields work on your parallel side. So those would be what we'd have in this situation. Okay, so now let's look at another one. Let's go to another page. New page. And let's see. Those are all forces. I think you can figure those out. Okay, here we go. Let's look at number 1. Okay? So on number 1, they tell us the solenoids, which are assumed to be close to each other, so they're close enough to feel one another. The resistance in the left-hand circuit is increased. Hang on just a second. I want you to be able to see both. Clear. The resistance, so the left circuit, R, goes up. Well, you guys know enough about circuits to know that if the resistance goes up, that means the current, the real current, goes down. Is that a change? Yes, that's a change in the behavior of the circuit. So what happens is we get induced stuff. So we have to think about what's going on here to figure out what our magnetic field is, what our electric field is, what our induced current is, and what our induced voltage is. We are making the current go down. Current is decreasing. So current goes down, so the induced current needs to be in the same direction as the original. If you trace the wire, that means that on the front loop, so we've got this, and it goes behind, and it front loops over, and it goes behind, and it front loops over. The current is going from the top of the battery up, and then on the outside it comes down and comes back to the negative part of the battery. So we have the front part is the going out, if you will, and the back part is the coming in. So what does that all mean? That means that we've got to figure out which way this current is flowing. So in the loop of wire, if you want to visualize this with me, which way would I point my thumb? Well, my thumb is coming up the back. My thumb comes up the back, and then my fingers wrap around so my thumb is here, my fingers have to wrap around like so. So my fingers point in to the magnet, because if I put my thumb on the back side, see how my thumb is on the back side, my fingers would be on the front side. That would mean that the magnetic field, when I put my thumb on the back and going up, my fingers point inside the middle from right to left. What that means is, if you think about this little tube, your magnetic field, this is what's happened. This is the real stuff on this side. What's happening on this side is this acts like the north and this end acts like the south. Okay? That's what's really happening. You'll notice there's no battery on the other one. So north to south. So our induced current will be still same direction as original, because it has to reinforce or replace the missing current. It also means that the battery on the right-hand side, the induced voltage, will be a battery that points this way. The voltage will point this way for your battery on the second resistor, on the second side. The induced electric field will be, due to the battery, will mean that the high potential high potential is on the bottom left, and low potential is on the bottom right. And then the induced magnetic field will also be trying to help. So if we decrease the current, the magnetic field feels a change going down, so the magnetic field will replace missing field. So in this case, what happens is, on the new right-hand circuit, here's what we get. I'm going to try to draw this like they've got it. So you come up the back and down the front, up the back, down the front, the back, down the front, down the front, through a resistor, and back home. So what we get is the right-hand circuit now acts like there is a battery here. Acts like there's a brand new battery here. And the current goes up on the back, down on the front, down on the front, down on the front, down on the front, through the resistor and back home. It means that it replaces the missing field, like so. So the little compass needle down here is going to, the compass needle will point towards north. So it will bend so that it turns that way. So my compass needle's end position will be over here. It'll point it north, because all compasses point it north. Okay, so what really happens? If you decrease something, the new ones, the induced ones, if you decrease the original, all the new ones do exactly what you saw to start with. They replace what is now missing. So what happens if you increase things? Well, if you increase things, then the new ones are going to oppose. They're going to make them go back down. So let's look at number 2. Same question. Okay, and then I'm going to do number 3, and then I'm going to quit for this video, because I think that'll be enough to get you through. So now we have a hole. So here's our hole, and we're going to take a magnet, and it's going to start over here, go through here, Now it's going to be out here, and we're going to move our magnet that way. So what is the change that is occurring? What is the real change? The magnetic field is getting weaker. Why is the magnetic field getting weaker? Well, you're moving the magnet away. The magnetic field is weakening because you're moving the magnet away. Okay, so B is going down. Now, let's go through what is the induced changes. Well, B induced needs to go up. E induced, I induced, and V induced we're going to have to talk about. So if my magnetic field, so this was north and this was south, how do I figure what happens with everybody else? Magnetic field weakening. Okay, magnetic field weakening. I have to do what it's already doing. So I have to north to south. My fingers point north to south. So my magnet went through here and now comes out the other side. So what am I seeing? I'm seeing a weakening magnetic field. So my induced is going to make a magnet that was not there before. Hey, I'm going to now have a magnet, and it's going to be north to south, just like that one, so you can feel like there's a field still there. Same direction. North to south, same direction. The electric field, what is that going to do to our electric field? Well, if our fingers were doing this, my thumb would be coming down the front. So my current is down the front. Current is down in front, up and back. So my induced current is going to do that exact same thing. Which means it's like we put a battery over here and connected to the back. And this connects to the front. And so the battery would be same direction for the battery. And once again, I've done another one where something is weakening. Number 2 was also a weakening situation. So the electric field will be from, will sort of go, what we call that, clockwise in the circuit. Current would be clockwise in the circuit. The field would point clockwise in the circuit. So there's a weakening one. Now, let's go on to number 3, which is now the other state. A magnet is dropped through a vertical copper pipe. Okay. I'm just going to pick. Let's let it fall like this. So north, south, and we're just going to let it track through the pipe. So, what's our real and what's our induced? The real is that I now have a stronger magnetic field. That's the real thing that changed. So what is it going to do to our induced things? The new induced thing is going to be weaken the field. My field was weak. It was small. I need it to stay that way. Maintain the status quo. So my induced magnet will actually point in the opposite direction. That magnet was not there to start with. This is an imaginary magnet. It's not imaginary. We see the effects for real, but it's weird. So imaginary magnet weakens it goes in the opposite direction. So it tries to put south pole by south pole. Say, stay where you were. Don't change. The electric field, now we have to figure out the current, because it's really the current that controls the rest of these things. So which way will the current go? Well, let's see. Originally, here's my copper pipe. North points this way. So my fingers, there's north. There's south is my wrist. North is my fingers. Okay? So my induced, that would make a clockwise, that would make a current so that my thumb points out here. So my current would be coming around. It will be coming around like so. and you can see that that for me is a counterclockwise. For you, for pointing at you, it's a counterclockwise, but looking down on it, it's counterclockwise. Okay, so the original, we're going to keep with purple for original. Originally, the current went like this, which means that now my new magnet goes this way. I have opposed your change. You're making me stronger. I'm going to force you to be weaker. And now my thumb's going to be on this side. Thumb will be over here. So for effect, let's show you what that means. So when I wrap my thumb here, now my thumb is going in the other direction. So in one case, my thumb was going clockwise. Now my induced current that was going, if I look at it from the top, if I go north to south this way, my current was clockwise. Now my opposite one is going to be counterclockwise. So current original is clockwise, and you just have to do this with your hand. I don't know how else to tell you, okay? So here's my wire. Here's my wire. My magnetic field does this. My thumb is going to point to the left in this case, which means my current will be going from this side to this side. And that motion, if you look from top down, is clockwise. So our new magnet is we flip this over, and now my thumb points out this side, so my current is going to go counterclockwise around the other direction to oppose the change. Now, instead of the battery phase, so that means that everything has to be counterclockwise. So the electric field has to switch directions, and the induced voltage will remove voltage from the circuit because it's trying to keep it low where it was to start with. And so that's how it works if you increase it. And I think I'm going to stop there for now, and we can ask questions about this next week or at one of the review sessions. I'll be happy to work with you. But those are our videos for today.